It's a very fine day and time to ponder over the delightful and all the more mystical colors spread across the canvas of the universe. Things painted as the blossoming tiniest form of life to the unperceivable colossal unexplored territory of the intergalactic space, all in the totality of everything that exists or ever existed. The mysteries of our universe are vast, and even with all our scientific and technological knowledge, we still have time to unravel the riddles of our existence. One of such is a black hole. A black hole is a region of space-time where gravity is so strong that nothing can enter the region, and not even light with zero mass can escape. Now we slowly leave the larger frontier and shift our gaze to the majestic Milky Way and our solar system, and here's our Earth. Engineers constructed these grand buildings as a symbol of power and supremacy. People build skyscrapers primarily because they are convenient. You can create a lot of real estate out of relatively small ground area, but ego and grandeur do sometimes play a significant role in the scope of the construction, just as it did in earlier civilizations. By definition, a shaft is a revolving rod that transmits power or motion. Its application of transmitting torque ranges from the simpler motor cars drive shafts to the marine propeller shafts. The gastropoda is the largest and most certainly the best known class of the molluscs. They are the most successful of the molluscan classes and occupy almost every habitat on Earth, from deserts to high mountains, fields, forests, lakes, streams, and oceans, and most probably your backyard.
Well, that was overwhelming. In these examples, we have seen examples of torsion in structures and members at different scales and magnitudes. So, what is torsion? It is a phenomenon which relates the internal shear stresses developed within an structural member to an angular load. Whenever there is an external torque applied to a member, it shows an internal response to it, same as the case of applied force, where the shear and normal stresses are the responses. This internal response of material due to the applied torque causes some deformation in it, which is the measure of shear strain. And the material is said to have some relative motion of its different cross sections, which is termed as twist. This twisting phenomenon of material by the applied load with some generation of shear stresses within it. As I have defined earlier, whenever an external torque is applied to a member and it goes some shear strain, the member is said to be in torsion. Now, in case of circular shafts, either hollow or solid, the relative motion of cross sections can be seen, but each cross-sectional area remains undistorted, that is, it remains circular throughout. This should be kept in mind, and this property does not hold for non-circular members.
This can be seen here in these two animations. There are two rods of different geometries and small boxes have been marked on both so the relative motion of cross sections can easily be seen. Now if I'll apply a torsional loading, they will undergo angular deformation and of course will be twisted. As you can see here in these animations, the boxes marked on the circular shaft has been rotated about the axis of the shaft, but they remain undistorted. While the square shaft, we have also experiencing a twist, but the boxes which we had marked for our understanding have been distorted.
We will restrict ourselves to the circular shafts only and try to develop some relations with the applied torque and the shear stresses generated.
For this, we will again consider a rod of cross section A and length L. Divide the whole cross section area into infinitesimally small large number of areas at a distance of rho units from the center of the rod. The differential amount of force dF would be appearing at each infinitesimally small area. Torque applied on the rod will be the integral of these differential forces computed over the entire area of the rod, or in mathematical form we can write it as integral of rho dF equal to T, where T is the applied torque. Since the forces applied here are always perpendicular to the axis and parallel to the area, we said that these forces will be causing shearing stresses inside the material. So we can relate the force dF by the shear stress in the following manner: dF equal to tau dA. By replacing this equation into the above relation, we say that integral of rho tau dA equal to T, where T is the applied torque again.